The late 1970s marked a transitional moment in commercial aviation engineering, a period in which analog assumptions were being quietly embedded into increasingly digital machines. The Boeing 767 was conceived as a product of that transition. It was designed to be efficient, resilient, and modern, a wide-body twin-jet optimized for medium to long-haul routes at a time when fuel economics and automation were beginning to dominate design philosophy. Its development reflected a growing confidence that human-machine interfaces, when simplified and standardized, could reduce error rather than create it. That confidence, while technically justified, masked a fragile dependency on procedural precision that would later prove unforgiving. Structurally, the aircraft represented a conservative yet refined evolution of proven Boeing methodologies. The primary airframe relied on high-strength aluminum alloys, selected for predictable fatigue cycles and well-documented crack propagation behavior under repeated pressurization loads. The fuselage frames and stringers were designed to distribute hoop stress evenly during each pressurization cycle, minimizing localized material failure. Wing structures incorporated fail-safe design principles, with multiple load paths intended to preserve structural integrity even under asymmetric aerodynamic loading. Nothing in the aircraft's physical architecture suggested vulnerability. On paper, the machine was robust, redundant, and forgiving. The propulsion system followed the same logic. Twin high-bypass turbofan engines provided thrust margins sufficient to accommodate single-engine operations at maximum certified takeoff weight. Fuel was stored in multiple tanks integrated into the wing structure, with cross-feed capability allowing balanced distribution and redundancy. Fuel quantity indication relied on electronic sensors converting fuel mass into displayed values, a critical distinction in an era when the industry was transitioning from volume-based to mass-based fuel accounting. The system itself was accurate within certified tolerances. Its weakness was not mechanical, electrical, or structural. It lay in the interface between engineering intent and human interpretation. By the early 1980s, the aviation industry was undergoing metrication in stages rather than as a unified transformation. Some fleets operated in pounds, others in kilograms, and many existed in a hybrid procedural environment where documentation, training, and ground operations were not perfectly synchronized. The Boeing 767 was among the first commercial aircraft designed to compute fuel requirements based on mass rather than volume, reflecting a more precise understanding of combustion physics and performance calculations. Fuel mass directly affects thrust-specific fuel consumption, climb performance, and range calculations. Engineers assumed that this shift would be absorbed seamlessly by operators. That assumption would later be tested under real operational pressure. On July 23, 1983, an Air Canada Boeing 767 prepared for a routine domestic flight from Montreal to Edmonton, with an intermediate stop planned in Ottawa. The aircraft itself was relatively new, accumulating flight hours well within its early fatigue life, far from any structural degradation thresholds. Environmental conditions were benign. There were no convective systems, no abnormal temperature gradients, no forecasted turbulence that would impose unusual aerodynamic loading. The flight profile was ordinary, the kind that rarely attracts scrutiny from engineers or investigators. It was precisely this normalcy that allowed the underlying failure to develop unnoticed. The ground handling environment, however, was less pristine. A fault in the fuel quantity indication system had been identified earlier, rendering the cockpit displays inoperative. Under standard procedure, this would require maintenance verification using dripsticks to manually measure fuel volume in the tanks. Volume, however, is not mass. To convert volume into usable fuel mass, a density factor must be applied. That factor varies with temperature and fuel composition but remains within known parameters. The conversion itself is trivial when units are consistent. It becomes catastrophic when they are not. Maintenance personnel calculated the required fuel using a density expressed in pounds per liter, while flight crew calculations assumed kilograms per liter. The numbers appeared internally consistent. Cross-checks, designed to catch gross discrepancies, did not trigger alarms because both sides were unknowingly using incompatible unit systems. No sensor failed, no valve stuck, no material exhibited fatigue cracking or thermal distortion. The aircraft was loaded with approximately half the fuel mass required for the planned route, yet all documented procedures appeared satisfied. From an engineering standpoint, this is where the illusion of safety solidified. The Boeing 767 systems were functioning exactly as designed. Fuel pumps delivered what fuel existed. Indications, though inoperative, were compensated for by approved manual methods. Performance calculations, based on assumed mass, showed adequate margins. The aircraft departed Montreal without any immediate sign of abnormality. Its climb profile matched expectations. Engine parameters remained within nominal ranges. There was no vibration indicative of compressor instability, no exhaust gas temperature anomalies, no fuel flow warnings because the system believed it was consuming fuel at expected rates relative to the assumed mass on board. As the aircraft cruised at altitude, the true state of the system divergence became increasingly consequential. Fuel flow rates, governed by thrust demand and aerodynamic drag, were higher than anticipated relative to the actual fuel mass available. Each minute of cruise consumed a larger fraction of the remaining fuel reserve than the flight management calculations predicted. Yet the absence of real-time fuel quantity indication masked this divergence. The aircraft was, in effect, flying on borrowed assumptions. From a structural and systems perspective, the airplane remained entirely intact. Pressurization cycles were stable. Cabin differential pressure remained within certified limits. The wing structure experienced normal bending moments under steady aerodynamic loading. There was no abnormal stress concentration, no onset of flutter, no thermal gradient capable of inducing material distortion. The machine was not failing. The system was converging silently toward a boundary condition its designers never intended to be crossed: total fuel exhaustion at cruise altitude. This is the critical distinction that defines the architecture of confidence in modern aviation. The Boeing 767 did not lack redundancy. It lacked semantic alignment. Engineering safety margins are predicated on correct inputs. When those inputs are corrupted at the procedural level, the machine becomes an amplifier of human error rather than a barrier against it. In this case, every calculation, every checklist item, and every assumption reinforced the same incorrect conclusion. The aircraft was safe because it appeared compliant with all known constraints. As the flight progressed westward, the remaining fuel mass dropped below thresholds that, under normal circumstances, would have triggered alerts. But alerts require sensors, and sensors require operational displays. The aircraft continued, structurally sound and aerodynamically stable, toward a point where the laws of physics would assert themselves without negotiation. Jet engines do not degrade gracefully in the absence of fuel. Combustion ceases abruptly, and with it, the entire energy ecosystem of the aircraft collapses. By the time the illusion began to fracture, the Boeing 767 was already committed to a trajectory that no amount of structural integrity or material resilience could correct. The architecture of confidence had done its job too well. It had allowed a fundamentally unsound premise to pass through layers of engineering excellence unchallenged, setting the stage for a failure that would not originate in metal, wiring, or software, but in the invisible space between units, assumptions, and trust. The aircraft entered the cruise phase under conditions that, from a purely aerodynamic and structural standpoint, were indistinguishable from thousands of uneventful flights conducted every year. At flight level, the ambient air density was low, reducing parasitic drag and allowing the wing to operate efficiently at a moderate angle of attack. The aluminum wing spars experienced predictable bending moments, well within elastic limits, and the distribution of aerodynamic loading across the span produced no asymmetric stresses that might have hinted at an abnormal state. The pressurized fuselage maintained its differential pressure smoothly, cycling through a stable equilibrium that imposed no unusual strain on frames or skin panels. Nothing in the physical behavior of the aircraft suggested impending failure. Yet beneath this apparent equilibrium, the system was already operating outside its true design envelope. Fuel flow rates, governed by thrust requirements and atmospheric conditions, followed the laws of thermodynamics with absolute indifference to procedural assumptions. Each engine consumed fuel mass proportional to thrust output, not to what pilots or dispatchers believed was available. The discrepancy between expected endurance and actual remaining fuel mass widened minute by minute, an invisible divergence that no structural sensor or aerodynamic indicator was designed to detect. The Boeing 767's fuel system architecture assumed that quantity indication would serve as the primary feedback loop, allowing crews to reconcile predicted fuel burn with observed depletion. When that loop is removed, the system becomes open-ended. Fuel pumps continue to deliver until they cavitate. Engines continue to operate until combustion chambers are starved of hydrocarbons. There is no gradual degradation curve, no fatigue cycle that produces warning cracks or progressive deformation. Fuel exhaustion is binary. Either the chemical energy exists or it does not. As the aircraft crossed deeper into its cruise segment, environmental conditions remained benign. Outside air temperature stabilized at values consistent with standard atmospheric models. Engine inlet temperatures stayed within nominal ranges, preserving compressor efficiency and preventing thermal stress that could otherwise induce material distortion or blade fatigue. Vibration signatures remained low, indicating balanced rotating assemblies and intact bearings. To any observer relying solely on mechanical cues, the aircraft was healthy. The first engine flameout occurred without precursor. From a systems perspective, this is not a failure mode that announces itself gradually. As fuel pressure dropped below the threshold required to sustain atomization and ignition, combustion ceased almost instantaneously. The engine's rotating mass, still possessing significant angular momentum, continued to spool for several seconds, producing residual thrust before windmilling took over. Electrical generators driven by the engine decoupled as rotational speed fell below operating limits, transferring load to remaining sources without immediate interruption. For the crew, the event manifested as a sudden loss of thrust accompanied by system alerts cascading through the cockpit. The aircraft's yaw response was modest, damped by the remaining engine and the inherent stability of the wide-body design. From an aerodynamic standpoint, the aircraft remained controllable. The wing continued to generate lift. Control surfaces responded normally. Structural integrity was uncompromised. The failure was localized entirely within the energy generation subsystem. Moments later, the second engine experienced the same fate. Fuel starvation is not selective. With no reserve remaining, both engines ceased combustion in rapid succession. The aircraft transitioned abruptly from powered flight to a pure glider, a configuration never intended as a sustained operational mode for a wide-body transport at cruise altitude. The aerodynamic loading profile changed instantly. Without thrust, airspeed began to decay, altering lift coefficients and shifting the balance of forces acting on the airframe. At this point, the aircraft's design philosophy revealed both its strengths and its limitations. The Boeing 767 possessed sufficient glide capability to remain airborne for a limited time, owing to its high aspect ratio wings and efficient aerodynamic profile. Lift-to-drag ratios, while inferior to those of purpose-built gliders, were adequate to convert altitude into horizontal distance under controlled conditions. The structure absorbed the new loading regime without complaint. There was no flutter onset, no control surface reversal, no evidence of structural resonance. The airframe was doing exactly what physics allowed it to do. The loss of both engines, however, precipitated a cascading systems degradation. With no engine-driven generators available, electrical power relied on battery reserves and the deployment of the Ram Air Turbine, a small propeller-driven generator that converts airflow into electrical and hydraulic power. This device, while reliable, provides only limited capacity. System prioritization logic shed non-essential loads automatically, preserving flight controls and critical instrumentation at the expense of redundancy and comfort. The cockpit environment narrowed to the bare essentials required to keep the aircraft controllable. Hydraulic systems, normally powered by engine-driven pumps, transitioned to backup modes. Control field changed subtly as pressures stabilized at lower values. Control authority remained sufficient, but margins tightened. Every control input now carried greater consequence, as energy management became the dominant constraint. Each degree of pitch adjustment altered the glide path, trading airspeed for altitude or vice versa. The aircraft was no longer forgiving. It demanded precision. From a forensic standpoint, This phase represents the anatomy of stress in its purest form. Not stress as measured in microstrain or tensile limits, but stress as an emergent property of interacting systems pushed beyond their assumed operating context. The wing experienced altered load distributions as the aircraft optimized for glide rather than cruise. The fuselage, still pressurized initially, imposed additional drag, complicating performance calculations. The flight crew faced a shrinking envelope defined not by structural limits, but by energy scarcity. The absence of thrust also eliminated bleed air, affecting pressurization and environmental control systems. Cabin pressure began to decay as the aircraft descended, though structural limits were never approached. The fuselage skin and frames were designed to tolerate far greater differential pressure fluctuations than those encountered during this emergency descent. Material failure was never a concern. The airplane was structurally overqualified for the challenge it faced. Its vulnerability lay elsewhere. Navigation now became a critical variable. With limited electrical power and no propulsion, the crew was forced to evaluate reachable landing options based on glide performance, wind conditions, and terrain. The aircraft's mass, reduced by fuel exhaustion but still substantial, influenced sink rate and maneuverability. Banking angles had to be minimized to preserve lift. Excessive aerodynamic loading from aggressive turns could have increased descent rate beyond recoverable margins. The aircraft demanded smooth, disciplined control inputs to remain within a survivable glide path. Throughout this phase, the Boeing 767 structure remained intact and compliant. There was no onset of material fatigue, no rivet failure, no skin buckling. The airplane was not breaking. It was being asked to perform a role it was never optimized for, yet its conservative engineering margins allowed it to do so. This is a crucial forensic insight. The absence of fuel transformed a highly automated transport into a large, heavy glider, but did not immediately compromise its structural integrity. The psychological stress imposed on the system's human operators, while outside the scope of material analysis, indirectly influenced aerodynamic outcomes. Control decisions affected load factors. Glide speed selection affected lift coefficients and induced drag. Each choice altered the stress distribution across the wing and tail surfaces. Yet, even under these evolving conditions, the airframe remained within elastic limits, absorbing the changing loads without any indication of incipient material failure. By the time the aircraft descended into denser air, aerodynamic forces increased, providing improved control responsiveness at the cost of higher drag. The glide ratio adjusted accordingly. The aircraft's fate now hinged on whether the remaining altitude could be converted into a controlled approach toward a viable landing surface. The stress on the system was no longer invisible. It was now explicit, measurable in feet per minute of descent and knots of airspeed. And still, the machine held together, structurally sound, awaiting the final test not of its materials, but of the assumptions that had brought it here. This phase exposes a fundamental truth about modern aviation systems. Stress does not always manifest as cracked metal or overheated components. Sometimes it exists as a silent divergence between reality and belief, accumulating until the margin for correction disappears. The Boeing 767 was not under-engineered. It was overconfidently contextualized, operating flawlessly within a framework that no longer reflected the physical truth of its condition. The transition from controlled glide to imminent ground contact unfolded as a sequence governed entirely by energy management and aerodynamic constraints. With both engines windmilling, the aircraft system stabilized into a degraded but coherent configuration. Control laws reverted to direct relationships between pilot input and control surface deflection, filtered only by hydraulic availability and aerodynamic effectiveness. There was no augmentation available to mask imprecision. Every movement of the control column translated into a measurable change in lift vector orientation, altering the balance between altitude loss and airspeed retention. As the aircraft descended, the increasing air density restored some aerodynamic authority, particularly to the elevators and ailerons. This improvement, however, came at the cost of a rising drag coefficient. The glide ratio deteriorated incrementally, forcing a steeper descent profile than originally projected at cruise altitude. The wing, now operating at higher lift coefficients to maintain controllability, experienced increased induced drag. Load factors remained within structural limits, but margins narrowed. The aircraft was no longer operating in a regime where inefficiency could be absorbed without consequence. Electrical power, constrained by battery endurance and the limited output of the Ram Air Turbine, imposed further restrictions. Instrumentation was reduced to essential flight parameters. Non-critical avionics were shed automatically. This simplification did not compromise structural safety directly, but it removed layers of situational awareness that normally inform precise energy management. The crew was forced to rely on fundamental aerodynamic cues rather than predictive systems. As the aircraft aligned itself toward a reachable landing site, the descent profile steepened further. Without thrust, the only means of modulating the glide path was through pitch and configuration changes. Extending high-lift devices would have increased lift at lower speeds, but at a prohibitive drag penalty. The decision space was constrained by the physics of the wing. Excessive drag would consume altitude faster than the remaining distance could be covered. Insufficient lift would result in accelerated descent and loss of controllability. The aircraft was balanced at the edge of its performance envelope. The landing gear deployment represented a critical inflection point. Mechanically, the gear was designed to be extended using alternate systems in the absence of normal hydraulic pressure. Gravity-assisted deployment ensured that structural locking mechanisms could engage even under degraded conditions. When the gear extended, the aircraft's drag profile changed abruptly. Parasite drag increased significantly, and the center of pressure shifted slightly, requiring compensatory pitch adjustments. Structurally, the gear bays and attachment points absorbed the loads without incident. They were designed to tolerate deployment at speeds and conditions well beyond those encountered in this scenario. The increased drag shortened the remaining glide distance dramatically. Sink rate increased. The aircraft's kinetic energy, already limited, was now being dissipated at a faster rate than anticipated. From a forensic standpoint, this moment defines the irreversible commitment to touchdown. The aircraft no longer possessed the energy required to adjust laterally or vertically in any meaningful way. All that remained was to manage attitude and descent rate to minimize structural loads at impact. As ground proximity increased, aerodynamic ground effect began to play a subtle but crucial role. The wing's induced drag decreased slightly as the aircraft entered the region where downwash interaction with the surface altered pressure distributions. This effect provided a marginal extension of the glide, flattening the descent angle just enough to reduce vertical speed at touchdown. It was not sufficient to restore control authority or arrest descent entirely, but it reduced the severity of the impending impact. The touchdown itself was not a single event, but a rapid sequence of load transfers. The main landing gear contacted the surface first, absorbing vertical kinetic energy through oleo strut compression. The struts, designed to dissipate energy through hydraulic damping and controlled deformation, performed within their certified parameters. Peak loads transmitted into the wing and fuselage attachment points remained below ultimate design limits. There was no immediate structural failure. The airframe flexed elastically, redistributing loads as designed. Almost immediately, the nose gear followed. The absence of thrust meant there was no capability for a go-around or thrust-assisted deceleration. Braking effectiveness was limited by available hydraulic pressure and the friction characteristics of the landing surface. Anti-skid systems, operating on reduced power, functioned imperfectly. Tire contact loads fluctuated as weight transferred forward during deceleration, increasing stress on the nose gear assembly beyond normal landing profiles. As the aircraft rolled, directional control became increasingly difficult. Without symmetrical thrust or full hydraulic authority, yaw control relied heavily on rudder effectiveness and differential braking. The rudder, effective at higher speeds, lost authority as airspeed decayed. Differential braking introduced asymmetric loads into the landing gear and lower fuselage structure. These loads were transient but intense, pushing certain components closer to their yield limits. The aircraft eventually departed the prepared surface, subjecting the landing gear to uneven terrain loads. Gear struts experienced lateral forces they were not optimized to absorb. One gear assembly collapsed as load paths exceeded structural tolerance. initiating localized structural failure. This failure was not due to fatigue or pre-existing material defects. It was a direct result of load magnitudes exceeding design assumptions for that operational context. As the gear collapsed, the lower fuselage contacted the surface. Abrasion and localized crushing occurred along the underside of the aircraft. Aluminum skin panels deformed plastically, dissipating energy through controlled material failure. Frames and stringers absorbed the loads, preventing catastrophic rupture of the pressure vessel. Fuel tanks, already empty, posed no combustion risk. The absence of fuel eliminated one of the most common post-impact hazards. The aircraft decelerated rapidly. Kinetic energy was converted into heat, sound, and material deformation. Structural members failed in a predictable hierarchy, with non-critical components yielding first. This progressive failure mode prevented sudden deceleration spikes that could have compromised occupant survivability. From an engineering perspective, the airframe behaved as a sacrificial structure, absorbing energy to protect the occupied volume. When motion finally ceased, the aircraft remained largely intact. The fuselage did not fragment. There was no in-flight breakup, no mid-air structural disintegration. The cabin structure preserved its shape, maintaining survivable space. This outcome was not accidental. It was the result of conservative structural design philosophies that prioritized energy absorption and redundancy. The moment of failure, when examined frame by frame, reveals an absence of traditional mechanical breakdown. No component failed due to fatigue cycle exhaustion. No material exhibited brittle fracture due to thermal stress or manufacturing defects. The engines ceased operation not because of mechanical malfunction, but because the chemical reaction sustaining them was no longer possible. The landing gear failed not because of hidden corrosion or metal fatigue, but because it was asked to absorb forces beyond its certified operational context. In forensic terms, this event represents a boundary condition breach rather than a component failure. The aircraft crossed from a regime of powered, controlled flight into a regime where its design assumptions no longer applied. Yet, even then, the structure responded in a manner consistent with its engineering intent. Failures occurred where they were expected to occur under extreme loading and in a sequence that mitigated overall damage. The significance of this phase lies not in the drama of the glide or the spectacle of the landing, but in the clarity it provides about system dependencies. The Boeing 767 did not fail because it was fragile. It failed because its operational framework allowed a critical variable, fuel mass, to be misinterpreted without immediate consequence. When the moment of failure arrived, it manifested not as a sudden explosion or structural collapse, but as a quiet cessation of energy followed by a controlled descent into the limits of physics. This reconstruction underscores a fundamental forensic insight. Catastrophic outcomes do not always originate in catastrophic failures. Sometimes they emerge from systems performing exactly as designed, faithfully executing instructions based on incorrect premises. The moment of failure, in this case, was not the engine flameout or the landing gear collapse. It was the point at which the aircraft's remaining energy dropped below what was required to sustain flight. Everything that followed was an orderly, if unforgiving, expression of that deficit. The forensic phase began not with wreckage recovery in the traditional sense, but with an intact airframe resting in an anomalous location, its structural narrative preserved rather than obliterated. This alone altered the character of the investigation. There was no debris field to map, no mid-air fragmentation to reconstruct. The aircraft had arrived at the ground largely whole, allowing investigators to examine failure progression sequentially rather than infer it statistically. For engineering analysis, this was an unusually transparent case. Authority over the investigation was shared between Canadian regulatory bodies and international observers, with participation from the aircraft manufacturer and engine suppliers. The event would later be formally catalogued as Air Canada Flight 143, though from a forensic standpoint the designation was almost misleading. Nothing about the aircraft itself suggested an incident in the mechanical sense. There was no evidence of structural compromise prior to landing, no material anomalies, no latent defects awaiting discovery. The airplane had not failed unexpectedly. It had complied faithfully with erroneous inputs. Initial external inspection focused on landing gear assemblies and lower fuselage structure. Deformation patterns were consistent with overload rather than fatigue. Metallurgical examination of fractured components revealed ductile tearing and plastic deformation, characteristic of sudden high-energy loading. There were no beach marks, no striations, no indications of progressive crack growth. This immediately excluded long-term material failure mechanisms, such as corrosion fatigue or stress corrosion cracking. The structural damage told a clear story. Components failed because they were asked to absorb forces beyond their certified envelope, not because they were compromised beforehand. Engine examination followed. Both turbofan units were disassembled under controlled conditions. Investigators found no foreign object damage, no blade tip rub indicative of bearing failure, and no thermal distress patterns associated with overtemperature events. Combustion chambers showed clean shutdown signatures rather than explosive flame-out damage. Fuel control units were intact and functioned normally during bench testing. The engines had not failed mechanically. They had been deprived of fuel. Fuel system analysis became the central axis of the investigation. Investigators examined fuel lines, pumps, valves, and filters. No blockages were found. Pump impellers showed no cavitation damage prior to flameout. Fuel control valves responded correctly when tested. The system, in isolation, was sound. Attention then shifted to the quantity indication system. The inoperative cockpit displays were confirmed, along with the maintenance deferral that allowed dispatch under manual measurement procedures. This deferral was legal, documented, and compliant with existing regulations. The dripstick measurements were reconstructed using recorded maintenance data. Investigators replicated the volume readings and applied the same density conversion factors used on the day of the flight. This exercise revealed the core discrepancy with clinical clarity. Maintenance personnel had converted volume to mass using a density factor expressed in pounds per liter. The flight crew, calculating required fuel mass, assumed kilograms per liter. Both numbers were correct within their own unit systems. The error was not mathematical. It was dimensional. From a forensic systems perspective, this represented a failure of semantic integrity rather than computational accuracy. The numbers aligned internally but diverged physically. When investigators recalculated the loaded fuel mass using consistent units, the shortfall became obvious. The aircraft had departed with approximately half the fuel mass required for the planned route. This was not a marginal deficiency. It was a gross energy deficit masked by procedural ambiguity. Investigators then examined organizational documentation. Operating manuals, dispatch forms, and maintenance logs were reviewed line by line. They revealed an environment in which metrication was incomplete and inconsistently applied. Some documents referenced pounds, others kilograms, often without explicit labeling. Training materials assumed familiarity with both systems, but did not enforce standardized usage. There was no mandatory cross-check designed specifically to reconcile unit systems across departments. The system relied on human intuition to bridge that gap. Simulator reconstructions were conducted to validate the sequence of events. Using recorded data and performance models, investigators recreated the fuel exhaustion timeline. The simulations confirmed that, given the actual fuel mass on board, flameout would occur at the altitude and geographic position reported. Flight performance matched observed descent profiles. There were no anomalies that required exotic explanations. The physics were straightforward. The airplane behaved exactly as expected given its true energy state. Laboratory testing extended to fuel quantity indication components. Sensors were calibrated and found to be accurate when operational. There was no evidence of drift, bias, or manufacturing defect. The inoperative displays were the result of a known fault, not a hidden systemic vulnerability. This distinction mattered. It meant the event was not the result of a latent technical defect waiting to surface, but of a procedural accommodation interacting with human assumptions. Human factors analysis, while secondary to structural and mechanical investigation, played a critical role in framing conclusions. Investigators mapped information flow between maintenance, dispatch, and flight crew. They identified multiple points where unit ambiguity could have been detected, but none where it was structurally guaranteed to be caught. Responsibility was diffuse. No single actor violated procedure egregiously. Each operated within an interpretation of the system that appeared valid locally. From an engineering ethics standpoint, This diffusion of responsibility is significant. Safety systems that rely on individual vigilance rather than enforced constraints are inherently brittle. The investigation highlighted that redundancy existed in quantity measurement methods, but not in unit verification. Redundancy without independence does not constitute resilience. Every layer shared the same implicit assumption about units, allowing the error to propagate unchallenged. The manufacturer's role was scrutinized carefully. Boeing engineers demonstrated that the aircraft's systems met or exceeded certification requirements. Fuel computation logic was correct. The decision to design systems around mass rather than volume was technically sound and aligned with emerging industry standards. However, the investigation noted that transitional risks during metrication had been underestimated at an industry level. The airplane assumed a world more standardized than the one it was introduced into. Regulatory findings emphasized this mismatch. The event did not expose a single faulty component, but a systemic vulnerability at the intersection of technology and human process. Recommendations focused less on hardware modification and more on procedural clarity. Mandatory unit standardization was proposed. Documentation was to be unambiguous. Training programs were revised to eliminate mixed unit operations wherever possible. Crucially, investigators rejected the notion that the incident was the result of simple human error in isolation. The term itself was deemed insufficiently precise. The crew did not miscalculate. They calculated correctly within an incorrect framework. The maintenance personnel did not mismeasure. They applied the wrong conversion constant in a system that failed to enforce dimensional consistency. The system as a whole allowed correctness to coexist with falsity. The forensic report concluded that no mechanical failure precipitated the loss of engine power. No material defect compromised structural integrity prior to landing. The aircraft met all applicable certification standards. The initiating cause was identified as fuel exhaustion due to incorrect fuel loading resulting from unit conversion errors during manual quantity calculation. Contributing factors included incomplete metrication, inadequate cross-check procedures, and over-reliance on human interpretation in a safety-critical interface. What makes this forensic aftermath distinct is its clarity. There was no ambiguity in causation, no unresolved technical mystery. The wreckage, the data, and the simulations all converged on the same conclusion. The airplane was innocent in the mechanical sense. It had been placed in an impossible situation by a system that allowed physical reality to be misrepresented numerically. From an investigative standpoint, this case reshaped how non-mechanical failures were conceptualized. It demonstrated that forensic analysis must extend beyond metal and wiring into the abstract domains of units, symbols, and assumptions. The aircraft did not run out of fuel because of leakage, contamination, or pump failure. It ran out of fuel because the system misdescribed its own state. This realization would have lasting implications. It forced regulators and engineers alike to confront the idea that future aviation risks would increasingly originate not from material failure, but from cognitive and procedural interfaces. As aircraft systems grew more automated and abstract, the margin for semantic error shrank. The forensic aftermath of this event thus became less about assigning blame and more about redefining what constitutes a failure in modern aviation. By the time the investigation concluded, the physical aircraft had already told its story. The metal bore no secrets. The engines held no surprises. The truth lay entirely in the invisible layer of interpretation that sat above the hardware. The forensic aftermath transformed a dramatic but survivable incident into a case study in systemic vulnerability, one that would resonate far beyond the specific aircraft and airline involved, reshaping how the industry understood the relationship between engineering precision and human meaning. The systemic legacy of this event unfolded not through a single corrective action, but through a gradual recalibration of how aviation understood the relationship between technology, procedure, and meaning. The aircraft returned to service after repair, its structure restored, and its systems verified. No fundamental redesign of the airframe or propulsion architecture was required. The metal had proven its adequacy. What required reconstruction was the invisible scaffolding of assumptions that governed how information moved through the system. Regulatory response focused first on unit standardization. Mixed unit operations, once tolerated as a transitional inconvenience, were reclassified as a latent hazard. Fuel planning procedures were rewritten to mandate a single unit system across dispatch, maintenance, and flight operations. Conversion factors were no longer left to memory or informal reference. They were embedded explicitly into documentation, with clear labeling and mandatory cross-checks. The objective was not merely to reduce the probability of error, but to make certain classes of error structurally impossible. This shift reflected a deeper philosophical change. Safety was no longer framed solely as the prevention of component failure or material degradation. It expanded to include the prevention of semantic ambiguity. Engineers and regulators acknowledged that modern aircraft operate as socio-technical systems, where numbers are as critical as rivets, and where misunderstanding a unit can be as consequential as miscalculating a stress margin. The event forced the industry to accept that correctness in isolation is insufficient. Correctness must be coherent across all layers of operation. Training programs were revised accordingly. Emphasis moved away from rote procedural compliance towards systems understanding. Crews and maintenance personnel were trained not just to perform calculations, but to interrogate their context. Why is this number expressed this way? What assumptions underlie this value? What happens if those assumptions are wrong? These questions became as important as checklist discipline. The goal was to cultivate a form of operational skepticism, a willingness to challenge apparent consistency when it rests on unverified premises. From a design perspective, the event accelerated efforts to reduce reliance on manual computation in safety-critical domains. Subsequent aircraft incorporated more robust fuel quantity indication redundancy, minimizing scenarios where crews would be forced to infer fuel state indirectly. Where manual procedures remained necessary, designers sought to constrain them with explicit unit enforcement. Interfaces began to display units prominently, reducing the cognitive load required to track dimensional context. The machine was asked to shoulder more of the burden of semantic clarity. This redistribution of responsibility between human and machine marked a subtle but important evolution in safety culture. Earlier generations of aviation had emphasized pilot skill as the ultimate safeguard. Later eras emphasized automation as a buffer against human limitation. The lesson of this event was different. It demonstrated that automation and human expertise can fail together if they share the same flawed assumptions. True resilience requires independence not just of components, but of interpretations. The regulatory community internalized this lesson. Certification frameworks began to consider human-machine interfaces as integral to system safety rather than peripheral concerns. The notion of pilot error as a terminal explanation lost credibility in cases where system design permitted plausible misinterpretation. Investigators and policymakers became more cautious about attributing causation to individuals when structural features of the system shaped their decisions. Accountability shifted from personal vigilance toward organizational design. The philosophical implications extended beyond aviation. This incident became a reference point in discussions about complex systems in other domains, from nuclear power to medicine. It illustrated how modern failures often arise not from broken parts, but from misaligned representations of reality. When systems become abstract, operating on symbols rather than direct physical cues, the integrity of those symbols becomes paramount. A kilogram mislabeled as a pound is not a small error. It is a distortion of reality that propagates through every dependent calculation. Within aviation, the event reinforced the value of conservative design margins, but also highlighted their limits. Structural robustness allowed the aircraft to survive an otherwise catastrophic energy deficit. Redundant systems preserved controllability long enough to reach a survivable landing. These margins saved lives, yet they could not compensate indefinitely for a fundamental absence of fuel. The machine could stretch physics, but not rewrite it. This reinforced an uncomfortable truth. No amount of engineering excellence can fully protect against errors introduced upstream if they remain undetected. In the years that followed, safety discourse increasingly emphasized the concept of latent conditions. These are vulnerabilities embedded within systems that remain dormant until specific circumstances align. The unit conversion ambiguity exposed here was precisely such a condition. It existed quietly, tolerated because it had not yet produced an adverse outcome. The incident demonstrated that the absence of accidents does not imply the absence of risk. Latent conditions accumulate invisibly, waiting for a catalyst. This realization reshaped how incidents were investigated and how near misses were valued. Events that ended without injury or loss were no longer dismissed as anomalies or attributed solely to good airmanship. They were mined for systemic insights. The question shifted from "why did this happen?" to "why was it possible for this to happen?" This distinction is subtle but profound. It redirects attention from outcomes to enabling conditions. The legacy also influenced how organizations approached change. The transition to metric units was no longer treated as a simple administrative update. It was recognized as a deep structural transformation that required alignment across technology, training, documentation, and culture. Partial implementation was understood to be more dangerous than delay. Consistency became a safety requirement rather than a bureaucratic preference. The cost of inconsistency, as demonstrated, could be existential. From an engineering ethics perspective, the event underscored the responsibility of designers to anticipate not just how systems will be used, but how they might be misunderstood. Designing for correct use is insufficient when incorrect use remains plausible and undetectable. The safest system is not the one that assumes perfect operators, but the one that constrains error pathways and surfaces contradictions early. This principle would later inform developments in cockpit design, software validation, and operational oversight. The aircraft itself became a symbol not of failure, but of endurance. Its ability to glide, absorb impact, and preserve life validated decades of conservative structural philosophy. Yet its story was never about metal or engines. It was about trust, trust in numbers, trust in procedures, trust that the system meant what it appeared to mean. That trust had been misplaced, not through negligence, but through overconfidence in implicit understanding. In reflecting on the cost of progress, the event occupies a particular niche. It was not a tragedy defined by loss of life, but a warning defined by proximity to it. It demonstrated how close modern systems can come to catastrophe while still appearing orderly and compliant. It revealed that progress, when measured solely in technological capability, can outpace the human frameworks required to manage it safely. The final lesson is neither dramatic nor comforting. It is austere. Modern aviation is safe not because it eliminates error, but because it recognizes where error can hide. When systems grow complex, the most dangerous failures are often the quiet ones, born of alignment rather than breakdown. The engine stopped because there was no fuel, not because something broke. The aircraft descended because gravity is relentless, not because lift vanished mysteriously. Everything that happened followed logically from an initial misrepresentation of reality. The cost of progress, in this context, was not paid in lives, but in humility. The industry learned that sophistication increases responsibility, that abstraction demands vigilance, and that meaning must be engineered with the same rigor as structure. The legacy of this event endures not in modified hardware, but in a recalibrated understanding of what it means for a system to be safe. Safety is not merely the absence of failure. It is the presence of shared truth.